All right, let's jump into another deep dive. This time, we're going to be looking at, well, it's a little bit of a cosmic detective story.
Oh.
Yeah, we're talking
Yeah.
about using the explosive deaths of stars to try to figure out how they're born.
Okay, so we're going way back in time.
Exactly. And we've got this really cool research paper that suggests there might be like a universal pattern, a blueprint for star formation, no matter where you look in the cosmos.
A universal pattern. That's a pretty big claim.
It is, right. And the crazy part is that it all comes down to these incredible events, supernovae and gamma ray bursts, these massive explosions.
Okay, I'm definitely intrigued. You know, the idea that we can trace those stellar explosions back in time, use them as clues to understand, those initial conditions that led to star formation billions of years ago, it's pretty mind-boggling.
Right. So we're basically talking about piecing together this giant cosmic puzzle using the remnants of these spectacular explosions.
I like that, a cosmic puzzle.
But I think before we get too deep into the puzzle pieces, we should probably define some terms.
Yeah, good point.
So this research is all about something called the initial mass function, or IMF for short.
Right, the IMF.
Have you ever heard of that? What does it mean?
Well, the IMF, it's a distribution. It tells us, what percentage of stars are born within certain mass ranges in a specific region, like where stars are forming.
So it's like a cosmic census. It's telling us the demographics of stars.
Yeah, exactly.
Yeah.
How many are big, how many are small, and so on. And getting that distribution, it's really crucial for astronomers because, a star's mass determines pretty much its entire life. How long it lives, how bright it shines, and, even how it dies in the end.
So if we can understand this IMF, if we can figure out this cosmic recipe for star formation, we're basically unlocking the secrets of stellar evolution, right? Across the entire universe. Okay, so that's a pretty big deal. But I still don't get how these supernovae and gamma ray bursts, these incredibly powerful explosions, how do they fit into all of this? It seems like a big jump, to go from those events to actually figuring out the IMF.
Yeah, it might seem like a leap, but trust me, there's a pretty brilliant logic to it.
Okay, well, lay it on me.
So like I was saying before, a star's mass basically seals its fate. Massive stars, they live fast and die young. And their grand finale, it's often a spectacular supernova.
Yeah, those are the ones that can basically outshine entire galaxies for a brief shining moment.
Right.
Just releasing this crazy amount of energy.
It's unbelievable.
And then you mentioned something even more extreme. You said gamma ray bursts.
Oh, yeah.
What are those exactly?
So gamma ray bursts, they're even more intense and short-lived than supernovae.
Mm-hmm.
And scientists think they're connected to the collapse of certain kinds of massive stars. What they do is they emit these beams of incredibly high-energy gamma rays, like the most energetic form of light to the whole universe.
Wow. Okay, that sounds intense.
But here's the key to it all. Both supernovae and gamma ray bursts, they leave behind these unique fingerprints, telltale signs that let astronomers estimate how massive the original star was.
Oh, okay. So by analyzing the aftermath of these explosions, these cosmic fingerprints, we can kind of work backward and figure out what kind of stars existed in that region a long, long time ago.
Precisely.
Even if those stars are, long gone.
Yeah. It's a bit like a cosmic detective story, really. We're using the evidence left at the scene, the supernovae and gamma ray bursts, to reconstruct the events.
I like that. So we're the detectives and the universe is our crime scene.
Exactly. And by counting the different types of explosions, we can work out the distribution of star masses that, must have existed in that region. Basically, we're mapping out the IMF.
Okay, so the researchers in this paper, they're using these incredibly complex models, right, to analyze all these explosions and try to figure out the IMF. And they're doing this in some really, really distant parts of the universe.
Right. We're talking about regions so far away that you can't even see individual stars.
Wow. So they're piecing together this puzzle with some serious missing pieces, but they're using these explosions as their guide.
It's a good way to put it.
But the big question, the one I'm really curious about, is what did they find? Does this IMF, this cosmic recipe for how stars are born, does it hold true across these mind-boggling distances?
Whoa.
Is it really a universal pattern, or do things get a little, messy out there in the distant universe?
Well, that's the really interesting part. What they found suggests that the IMF in those distant regions, it actually looks a lot like what we see closer to home.
Wait, so you're saying no matter where you look in the universe, whether it's our own galactic backyard or, billions of light years away, stars are born following the same basic rules.
It seems that way. It points to this possibility of like a universal IMF, a sort of, I don't know, a cosmic rule book for star formation across these huge stretches of space and time.
Okay, that has some pretty big implications, right?
Absolutely.
Like what? Give me some example.
Well, if the IMF really is universal, then we can start making much more accurate predictions about how galaxies evolve, how the elements are spread out in the universe, even the conditions that might lead to planets forming and, maybe even life.
Wow. So by studying these exploding stars, we're not just learning about their deaths, we're getting insights into like the whole evolution of the cosmos.
Exactly.
But I gotta ask, are there any scientists who are like skeptical about this whole universal IMF thing? It seems almost too perfect, you know?
Oh, of course. Healthy skepticism is crucial in science.
Right.
And some researchers, they argue that while the IMF might be generally consistent throughout the universe, there could be these subtle variations depending on the specific conditions in a star-forming region.
Okay, so it's not a one-size-fits-all situation.
Not necessarily, no.
So there might be a little wiggle room, some like cosmic fine-tuning depending on the local environment.
Right. It's like, the basic recipe for bread is basically the same everywhere, but you can tweak the ingredients a little, change the oven temperature, and you end up with a slightly different result.
Yeah, that makes sense. And there's those subtle variations. They could actually tell us a lot about like the forces that shape how stars are formed, right?
Exactly.
Right.
It reminds us that the universe is this dynamic, constantly changing place, full of surprises and little variations.
I love these deep dives. We start with this like seemingly simple question, how are stars born? And we end up down this rabbit hole of like cosmic connections and mind-blowing ideas.
It's true.
And speaking of mind-blowing tools, what about telescopes like the James Webb and the Euclid telescope? They seem to be making headlines all the time.
Yeah, those are real game changers. They're giving us this like unprecedented view of the universe. We can see distant galaxies and stellar explosions in so much more detail than ever before.
Wow. And that data, that's going to help us test and refine our understanding of the IMF, right?
Yeah.
Including those, those potential variations we were just talking about.
Exactly.
So we're on the verge of a golden age in astronomy with these powerful telescopes.
It really feels that way.
So what are like the big questions that scientists are trying to answer using these new tools?
Well, one of the biggest ones is what drives the IMF. Like, what are the fundamental physics behind it? Is there some law of physics that dictates how stellar masses are distributed? Or is it, this super complicated interaction of factors that varies from place to place?
So we're trying to crack the cosmic code.
Basically, yeah.
Yeah.
We want to find that underlying blueprint for how stars form.
That's a pretty big task.
It is.
But it sounds like we're getting closer, with each new discovery.
We are. And each piece that we find brings us closer to understanding our own place in the universe.
Right. Think about it. The elements that make up our bodies, the atoms, they were created in the hearts of stars billions of years ago.
It's amazing, really. Understanding the IMF is about understanding our origins, tracing our lineage all the way back to those very first stars that lit up the universe.
That's a beautiful way to think about it. And it reminds me of that famous Carl Sagan quote, "We are made of star stuff."
Oh, it's so true.
So even though this research might seem super abstract at first, it's really all about us, our origins, our connection to the vast web of existence.
Exactly. And I think, beyond that, there's this deeper philosophical layer to it all. We search for patterns in the universe, whether it's the IMF or the laws of physics. And it's a reflection of this, this human desire to find meaning in the chaos. We want to connect to something larger than ourselves.
I love that. It's like we're putting together this giant cosmic jigsaw puzzle, and the IMF is one of the key pieces. But as we start to fit those pieces together, we realize the puzzle is even bigger and more complex than we ever imagined.
That's the beauty of it.
And that sense of wonder, that's what makes it so compelling, right? The desire to keep exploring and discovering.
Definitely. The universe is full of these mysteries, and the IMF is just one example of how much we still have to learn. But the more we explore, the more we realize that the journey itself is the real reward.
So we've been talking about this potential universal pattern in how stars are born, but are there any exceptions, any outliers that challenge this idea?
Well, there are always exceptions, aren't there?
Yeah.
And in the case of the IMF, those exceptions, those outliers, they can be really interesting. Like some studies, they suggest that in really dense environments like the centers of massive galaxies, the IMFs might be skewed. toward having more massive stars.
Oh, so in these, like, cosmic cities, the stars are living life in the fast lane,
You could say that.
burning bright and dying young.
Yeah. It's like the Cosmic Cookbook has some, like, alternative recipes.
Right, depending on the local conditions.
Exactly. And think about what that could mean. If we find these regions where the IMF is totally different, it could point to some really exotic astrophysical processes, stuff that we don't even understand yet.
Exotic astrophysical processes. Doesn't that sound exciting?
Very exciting. Maybe there's this unique mix of gravity, turbulence, and magnetic fields in these extreme places that, changes how stars are born.
So the basic recipe for bread is the same, but add a pinch of this, a dash of that, and suddenly you've got a whole new flavor.
A perfect analogy. What other cosmic ingredients are out there, just waiting to be discovered?
That's the big question, isn't it?
And that's where things get really interesting. We're entering this new era of exploration with these amazing telescopes, James Webb, Euclid. With their power, we can peer right into the hearts of galaxies, study the environments around supermassive black holes, and look for those little variations in the IMF, the ones that might point to new physics.
Wow, okay. So we've talked about this universal IMF, the possibility of variations, and these super powerful telescopes that are helping us uncover all these secrets. But I want to step back for a second. Why should, the average person care about any of this? Like, what makes this research relevant to our everyday lives?
That's a great question. And I think at the heart of it, studying the IMF, it's about figuring out our place in the cosmos. It's about tracing our lineage back to those very first stars, the ones that created the elements that make up everything around us, our bodies, the planet, you name it. We're part of this huge cosmic story.
Right. We're all connected to the stars and galaxies, even if we don't always think about it.
Absolutely. It's more than that. It's about this deeper philosophical idea, too. We search for patterns in the universe, the IMF, or the laws of physics, because I think deep down, humans want to find order in chaos. We want to feel connected to something bigger than ourselves.
We want to solve the cosmic puzzle.
Yeah. But as we put the pieces together, we find that the puzzle is even bigger and more complicated than we imagined. And that's what's so amazing, that feeling of wonder, the drive to keep exploring and discovering.
It's the journey, not the destination.
Exactly. The universe is full of mysteries, and IMF is just one small part of it. But the more we learn, the more we realize how much we don't know. It's about embracing the unknown and asking those why questions.
So to everyone listening, keep looking up at the night sky, keep asking those questions, and don't ever lose that sense of awe.
The universe is a pretty incredible place.
Yeah.
And there's always something new to discover right around the corner.
This has been a fascinating deep dive. We talked about exploding stars, this potential universal pattern and how they're born, and how it all connects back to us. Until next time, keep exploring, keep wondering, and keep looking up.